Having seen how object detection was performed in the pre-deep learning era, as well as how basic CNNs can be adapted to object detection, let's now move to how object detection is done today in terms of contemporary methods. Existing methods that obviously are based on top of CNNs can be broadly divided into what are known as region proposal based methods and dense sampling based methods. So we will cover region proposal based methods in the rest of this lecture and take up dense sampling methods in the next lecture. In region proposal based methods, the framework is composed of two stages. In the first stage, there is a network or a module that proposes different regions that could contain objects. And in the second stage, a classifier, in our case a CNN, takes those regions and classifies them as belonging to an object or could even belong to the background. This is more robust in performance but is slow because of the two-stage approach. On the other hand, dense sampling based approaches are a single stage approach where the proposal of regions and the classification or detection of those regions into objects is all done in one shot through a dense sampling procedure. This is simpler and faster, but sometimes can fall short of the accuracy when compared to region proposal methods. Let's now discuss region proposal methods. So the earliest one was known as the RCNN or the region-based CNN, which was proposed in CVPR of 2014 by Ross Gershik. This approach has a first stage where it uses a method known as selective search, which is an image processing method. It doesn't use a neural network for that, but using a selective search approach, it proposes several regions that could have objects. Each of these regions is then evaluated by a CNN to perform classification as well as do bounding box regression to get the correct localization inside those region proposals. Remember, when we talked about overfit, we said that we could divide these into two heads. We will continue to use that for all detection methods that we will see. How do you do that first stage, selective search? So the selective search module uses a graph-based image segmentation or a mean shift-based image segmentation to get an initial set of region hypotheses. So these hypotheses are then hierarchically grouped based on region similarity measures like color, texture, size, region filling, so on and so forth. So if you used color for grouping up regions, you may end up getting an object such as this. If you used texture for grouping up regions, you may get a region such as this. Or if you used region filling, you may end up getting a region such as this. In practice, you have an image. You use an existing segmentation method. We covered this in initial weeks. You will get various different segments that you see here. Then you combine these segments using agglomerative clustering, if you recall, using either color cues, texture cues, or region filling cues, or any similar cues. And this gives us regions of a larger scale. Now, how do we use these regions? Once you get these region proposals, this particular method selects 2000 such region proposals. So by combining and coalescing different subregions, you get somewhere around 2000 region proposals. Each of these region proposals are warped to the same size. Why do we need that? Because we're going to give that as input to the CNN. And remember, the CNN can only take a fixed input size as its input dimension. You cannot give a 20 x 20 image and a 100 x 100 image. A CNN can only accept one size. That's the nature of the architecture that we use. So whatever be the size of the region proposals, they are all warped to make it the same size. So there could be some artifacts of stretching because of this. And these proposals are then given to a CNN. So in this particular work, the CNN was like an AlexNet or a VGG. Then you get feature maps out of the CNN that goes through a fully connected network. And then there are three components. You have a softmax component that does classification of each of these regions into one of the known classes that you're looking for while performing detection. It also has an SVM which is actually used for classification. We'll explain that in a moment. And finally, it also takes the feature maps through a different fully connected layer to perform bounding box regression. I'll repeat that this bounding box regression step that you see here does not, you already have a region given to you. Remember that this region is a part of the original image. So what the bounding box regression module does here is to give you the offset from this region in the original image to the correct bounding box. So if this region was in specific location of the original image, the bounding box regression module may give values such as +1, -2, and maybe +3, -4, which means that the top left corner should be moved by 1 pixel further on the x-axis, moved by 2 pixels to the left on the y-axis, and the height and the width must be adjusted by +3 and -4, so on and so forth. So this bounding box module, regression module, predicts the offsets from the current location of the box that you have. Now let's see the entire training procedure. So in the first step, you consider all of these modules, the CNN, the feature maps, the fully connected network, and you fine-tune this fully connected network to the warped images using a softmax and a cross entropy loss. We generally refer to cross entropy loss also as log loss, because when you have multiple classes, your cross entropy loss turns out to be simply the log of the probability of the ground truth class. Why so? Because you would have your cross entropy loss to be given by yi summation over I, yi log pi. This is your cross entropy loss. Remember that your ground truth is going to be 1 only for the correct class and is going to be 0 for all other classes. So you'll be left with just minus log pi, no summation. And that's why we sometimes call cross entropy loss as just log loss, because when you use it for a multi-class classification setting, that's what it turns out to be. So that's the first step, to tune the CNN. So you already initialized the CNN with weights of an AlexNet model or a VGG model. Now you further refine those weights by using a log loss and the softmax in the last layer through the fully connected network and the feature maps. In the second step, you now take the outputs of the fully connected neural network and use them as representations of each of these regions, and then train a class-specific SVM depending on the number of classes in your detection problem. You could be detecting, say, up to 20 different kinds of objects or even further. You would then learn 20 different SVMs based on the features that you got as output of the fully connected network. And then the SVM is then used to make the final decision of the class in that region. And the stage 3 is training the fully connected layer for performing bounding box regression, where one would use L2 loss or the mean square error loss. Remember, they both are synonymous. What are the limitations of RCNN? Firstly, it is a multi-stage pipeline of training. As we just saw, you have to first train one head, then you have to take representations and train 20 different SVMs or as many different SVMs as classes, and then you also have to train a bounding box regression head. Can we make this simpler? We'll see this in a minute. But before that, the extraction of region proposals initially could require a lot of time and space. Remember, we have to do segmentation, coalesce them, and then finally pass each region proposal through the CNN and get your classification, bounding box offset, so on. A data set such as Pascal VOC, which has 5,000 images approximately, required about 2.5 GPU days and several hundred GBs of storage, which can turn out to become impractical. And using RCNN, at test time, the object detection took about 47 seconds, which is not really real time. This led to the development of the fast RCNN approach by the same authors, in fact, and it was published in ICCV of 2015. In this case, there were a couple of different innovations that were introduced. One idea was, while we still do selective search to get the region proposals, we would map these region proposal locations directly to the feature maps after sending the full image through the CNN. If you go back and see how it was done earlier, each region proposal was fed individually to the CNN, but now we are saying that we'll feed only the entire image to the CNN. This helps us because otherwise we had to do 2000 forward propagations, where 2000 are the number of region proposals, through the CNN. Now we just need to do one forward prop through the CNN, which is the entire image. Through selective search, we would get a lot of region proposals. We now map, because the region proposals have certain coordinates in the original image, you can map those coordinates to the feature maps that you get as the output of the CNN. And once you get these feature maps, you have two heads, one for classification where log loss is used, one for bounding box regression where L2 loss is used. No more need for SVMs, which seems obvious, but that's how this method was improved. So now, how is the region of interest projected? So we said that you take these region proposals that are outputs of the selective search approach and map them into the feature maps. How would you do that? If this was one of your region proposals, let's assume that the 6x8 patch was a region proposal in your original image. Then remember that your CNN follows a set of steps where the image gets, in most likelihood, downsized as you go through each iteration, because if you perform convolution, the image size reduces. If you perform pooling, it further reduces, and so on. So you take the same region proposal's dimensions, keep forward propagating it through a similar set of operations, and you would notice that this 6x8 patch matches to this 2x3 patch on the feature maps. As a next step, after projecting the region proposals onto the feature maps, we need to bring all of these region proposals to the same size, for the same reason that we said that the next layers can only take input of the same size. To do this, fast RCNN proposes a module known as ROI pooling. ROI stands for region of interest again. The ROIs can be of different scales, so to get a scale invariant way of pooling. So what ROI pooling does is, given any region which is, say, of size small h cross w, it converts it into a region of capital H cross capital W grid of sub windows, with each sub window of size h by capital H and w by capital W. So for example, if you had an 8x8 region and your target size was 2x2, you would accordingly divide this 8x8 into a 2x2 grid and do pooling inside each of these 2x2 regions and get your output in the target location. So your pooling here would happen in this location. You would do, say, a max pooling, and only the max value would go here, so on and so forth. So if you had a 4x6 region of interest, then you would still have to do a 2x2, you would still want a 2x2 output. So you divide it this way now, and you pool across all of these 6 pixels, and that value goes here. So that's how ROI pooling works. And once ROI pooling is done, you then send it through further layers, fully connected layers, and at the end of which you have 2 heads with 2 different loss functions. So you have a multitask loss, one task for classification and one task for regression. So if we assumed that U is the true class and V are the ground truth bounding box regression targets, if P is the predicted class probability and TU are the bounding box regression offsets for the true class, then the loss for each region of interest would be the classification loss plus your localization loss. By localization loss, we mean the bounding box regression loss. The classification loss, as we just said, is given by minus log PU. The cross entropy loss simplifies into a log loss. And the localization loss is prefixed by an indicator function which states that we're going to compute this only for the true class. For the other classes, we don't need to compute this kind of a localization. That's what the indicator function dictates. What is the localization loss in fast RCNN? Earlier, we said we typically use the L2 loss, but in fast RCNN, the method recommends the use of a new loss known as the smooth L1 loss. Note that L1 loss is the sum of the pairwise differences between dimensions and their corresponding absolute values, and this is used instead of the L2 loss. And a smooth version of the L1 loss. Remember that L1 loss, any absolute value function looks somewhat like this. That's the f of x is equal to absolute value function. But this function can become non-differentiable at 0. So to avoid that, you have a smooth variant of the L1 loss known as smooth L1 loss, which is given by 0.5 x square if x is less than 1, otherwise x minus 0.5 otherwise. So this would give you a slightly smooth, when it comes close to the 0, it becomes quadratic. So you would have a slightly smooth function, but otherwise it's absolute value or L1 everywhere else. Why smooth L1 loss? Okay. It turns out that smooth L1 loss is less sensitive to outliers than L2 loss. Why is this so? Is homework for you, and we'll discuss that in the next lecture. So the summary of fast RCNN is, given an image, you still have selective search. You also forward propagate the full image through the CNN, say an AlexNet or VGG, whose output gives you a depth of feature maps like the output of any convolutional layer. Now you project all the region proposals that you got through selective search onto these feature maps. This avoided, as we said, multiple forward propagations through the convolutional layer. Then you perform ROI pooling to get all those region proposals to the same size. You then send this through a fully connected network, which has a softmax head or a classification head and a bounding box regression head. With these improvements, fast RCNN significantly outperformed RCNN in training time and test time. Fast RCNN took about 8.75 hours for training, while RCNN took 84 hours for training. That's a 10x reduction. Importantly, at test time, while RCNN took 47 or 49 seconds for doing detection on each image, this came down to 2.3 seconds for fast RCNN and just 0.3 seconds if you had to avoid the region proposal finding step. So that gives us a clue on what needs to be done next, which is we have to find a way of avoiding the process of getting region proposals using selective search, because among the 2.3 seconds, it looks like 2 seconds is required just for that step. This leads us to faster RCNN. Faster RCNN replaces selective search with a region proposal network. So instead of getting region proposals through segmentation methods that are offline, we're going to try to see if this can also be done as part of the neural network itself. This was proposed in NeurIPS of 2015, and let's see how this is done. So given an image, you forward propagate the image through a CNN like AlexNet or VGG. You get a set of feature maps. Now these feature maps are provided to the region proposal network, whose job is to tell us which regions are likely to have an object. It does not worry about classifying the object, it only worries about objectness of a region. And these regions are then provided through an ROI pooling layer. That part of it is very similar to fast RCNN. And finally, you have classification and bounding box regression, just like how we had it with fast RCNN. How does the region proposal network work? It uses what are known as anchor boxes of different scales and aspect ratios to identify multiple objects in a given window. Let's see how that works. So given a particular window, so let's say any particular window in an image, so it takes different predefined anchor boxes. So you can define an anchor box which is defined given a particular location. You can define an anchor box that's given by this rectangle here. You can define an anchor box that's given by this rectangle here, and you can define an anchor box that's given by this rectangle here. So these are a set of predefined rectangles which, given the center, can define several kinds of regions around that center. What does the region proposal network learn? It has its own loss function to learn that part of the network. Recall InceptionNet. Recall that in InceptionNet we had certain loss functions at different stages of the network. You could consider this to be similar to that. So here the output expected of the region proposal network is any of these anchor boxes an object? So you're only looking for object or not an object, right? So there are no further classes. It's a binary classification problem. And if you had k anchor boxes, which as I just mentioned are predefined, you have to define them when you start. And if you had your depth to be, if you had 512 cross 20 cross 15 to be your image features, then you're going to have k cross 20 cross 15 as the output. And you would have 4k cross 20 cross 15 as the bounding box offsets for each of these anchor regions. So this part of the network does do a bounding box offset recognition or fine tuning, but it also checks whether a region is an object or not an object. Let's then see what happens. Okay, so you're going to have a fully convolutional layer which does objectness classification and bounding box regression. So in this case we are talking about, say, 9 anchor boxes, which is what was k on the previous slide, but this could be different based on what one chooses to do in a given setting. So in the first step, you take the input image, you take a CNN pre-trained on AlexNet, use the feature maps, send it through a region proposal networks, which is a further set of convolutional layers, and check for objectness and bounding box coordinates and train this region proposal part of the network. You can fine tune the previous weights too. This is step 1. In the second step, you take these region proposals obtained from the region proposal network, feed that onto the feature maps. Those are going to be your regions now. The rest of it stays very similar to fast RCNN, and you train all these weights using your classification loss and bounding box regression loss, where now the classification loss tries to categorize a region into any of, say, 20 objects or how many ever objects you have in a given problem setting. So this is the second step, which is very similar to what is done in fast RCNN. In step 3, the CNN is made common for your entire network as well as the region proposal network. So you share those parameters and you train your RPN while freezing your CNN parameters to help improve the RPN's performance. And finally, in step 4, you freeze everything else in the network and only fine-tune your FC networks to get your final classification output and bounding box offset regression outputs. This is the 4-step training procedure proposed by Faster RCNN. And using this approach, the test time speed reduces from 2.3 seconds to 0.2 seconds, which becomes closer to real time for every image. The homework for this lecture would be to go through the Viola-Jones object detection framework and a very nice write-up on called Object Detection for Dummies, linked here. And if you'd like to understand overfeed, here is a link. There is also a nice video series on evolution of object detection models if you like. And here is the exercise that we left for you. Smooth L1 loss is less sensitive to outliers than L2 loss, as was proposed in Fast RCNN. Can you try to find out why? The next lecture, we will talk about dense sampling methods for object detection.